understand? Any questions?
Why are we studying these differential equations? This dy, dx, x, y. Where am I going to use this in the real world? No interviewer is going to ask me to solve a differential equation and then say, "Sir, discuss करने क्या?"
Oh, beta, don't worry, I will teach you.
Oh, hello. I'm still here.
Okay, so you must be wondering where the word homogeneous comes from. So homogeneous means of the same kind or nature. So in mathematics, it signifies a consistent structure or relationship between terms. The term homogeneous was first applied to differential equations by a Swiss mathematician Johann Bernoulli. He used it to describe a type of first order differential equation that could be simplified and solved using a specific substitution. So you must be wondering, if we have homogeneous, there should be homogeneous functions as well. You're right. A function is said to be a homogeneous function of x and y with degree k if f of tx comma ty is equal to t to the power k times f of x comma y, which means that the power of each term is the same. Using this, we go to homogeneous differential equations. So all the differential equations of type dy by dx is equal to f1 x comma y by f2 x comma y, where f1 x comma y and f2 x comma y are both homogeneous functions of x and y of the same degree. We call them homogeneous differential equations. So can you think of an example, Vasu?
Okay, so for example, dy by dx is equals to x square plus y square divided by xy. How do we solve this?
That's a very interesting question, and you should remember that the first step in solving first order homogeneous differential equation is to use the substitution y is equal to vx. So why do we use it? We use it because it transforms our equation into a much simpler form, and then later we can use it using the variable separable method. Now our step 2 would be that because v and y are both functions of x, we can differentiate y is equal to vx with respect to x using the product rule. So now we get dy by dx is equal to v plus x times dv by dx, and say that this is equation 2, and the equation we saw in the previous slide is equation 1. We use both the equations 1 and 2 and we substitute them into our original homogeneous equations that we have in terms of f and f of x comma y. So can you build on that, Vasu?
Okay, so we can write this equation as v plus x dv by dx is equals to 1 plus v square by v. After simplifying, v plus x dv by dx is equals to v plus 1 by v. After separating both the variables, we can write it as x dv by dx is equals to 1 by v.
Yes.
After integrating, we can write it as v square by 2 is equals to log x plus c.
Very good. Lastly, do not forget to substitute back y is equal to vx in terms of v is equal to yx, so that you get the solution for y in terms of x. So can you do that for me?
So after replacing v is equals to y by x, we get our answer as 1 by 2 v y by x whole square is equals to log x plus c.
Very good. So do you see that graph over there?
Yes.
So if we try to understand it mathematically, so homogeneous ODEs always link back to the idea that scaling doesn't change the slope pattern. That's why solutions look symmetric about the origin. You see in the graph, they are like rays of light from the sun, except the sun here is the origin and you won't get a tan. So our next concept is reducible to homogeneous differential equations. I'm not sure if I can explain this to you. Maybe we should ask our teacher. What do you say?
Yes, we should.
What, man? What were you doing in class? Were you sleeping or looking outside the window when I was teaching? Oh, this is the last time I'm going to teach you again.
Okay, students, I'll be explaining reducible to homogeneous differential equations. Now, when we're dealing with first order differential equations, which is not homogeneous, we can simplify it to a homogeneous equation. This is only possible where f of x comma y is equals to ax plus by plus c divided by capital AX plus capital BY plus capital C. The method for reduction depends on the relationship between the two linear expressions in the numerator and denominator. Now we have two cases. Case 1, which is a by a equals to b by b, and case 2, which is a by a is not equals to b by b. Now let's start with case 1, which is a by a is equals to b by b. I'll explain this using an example where dy by dx equals to x minus y plus 3 divided by 2x minus 2y plus 5. In such cases, we use ax plus by equals to b. This is a general form where a is equals to 1 and b is equals to minus 1. Rewriting this, it will become y equals to x minus v. Now when we differentiate this with respect to x, we get dy by dx equals to 1 minus dv by dx. Simplifying this, we get dv by dx equals to v plus 2 divided by 2v plus 5. Now, using variable separable and integrating it, we get x minus 2y plus log x minus y plus 2 equals to c. Did you guys understand?
Yes.
Yes.
Okay, that's great. Now, moving on to case 2, which is a by a is not equals to b by b. Again, I'll explain it using an example. 2x plus y plus 3 dx is equals to 2y plus x plus 1 dy. In such cases, we equate x equals to capital X plus h and y equals to capital Y plus k. Now, when differentiating this, we get dy by dx equals to 2x plus h plus y plus k plus c divided by x plus h plus 2 into 4 plus k plus c. Now, when we simplify this, we get 2x plus y plus 2h plus k plus c divided by x plus 2y plus h plus 2k plus c. Now, in the next step, we take the terms of related to h, k and equate it to 0. Here we have 2h plus k plus 3 and h plus 2k plus 1 equals to 0. Now, using simultaneous equations, we arrive at k equals to 1 by 3 and h equals to minus 5 by 3. Now, from here onwards, it's the usual way of solving homogeneous differential equations, which you can try it out during your free time. Before you try it out, do you guys know anything about the applications of homogeneous differential equations?
Oh, I know. We can apply the concept of homogeneous differential equation in the field of economics and physics. In economics, we can apply it in constant returns to scale. A production function f of x, y has constant returns to scale if increasing all inputs by certain proportion results in proportional increase in output. A production function that satisfies f of tx, ty is equals to t to the power k f x, y is specifically known as linear and homogeneous function of degree 1. The concept of homogeneous function of degree 1 directly corresponds to the economic principle of constant returns to scale. In physics, we can apply it in thermal conduction for heat transfer in a rod or slab. If there are no internal heat source, the temperature distribution over space and time obeys homogeneous heat equation, a form of partial differential equation.
Oh yes, and it's also applied in biology and chemistry as well. So in biology, population growth or the Malthus model is a prime example of the use of homogeneous differential equation. So for unlimited resources and no external effects, the rate of population or bacterial growth is modeled by a first order homogeneous differential equation which predicts exponential population increase. This is a classic model in ecology and epidemiology, providing baselines for more complex resource limited scenarios. In chemistry, radioactive decay is an example. The decay of radioactive materials is exponential and modeled by a first order homogeneous differential equation. This fundamental process underlies radiometric dating, nuclear power management, and medical imaging.
That's very good, Basu and Arpan. Now, Since in the beginning of our class, Vasu did not understand homogeneous differential equations, I have a question for you. The question reads as such. Along a long straight river, cumulative upstream discharges and turbulent mixing causes the pollutant concentration P of x in mg per liter changes with downstream distance x in kilometers. A simplified Plume model suggests that the rate of change of concentration is dp by dx equals to x squared plus p squared by xp, where x is greater than 0. If at x equals to 1 kilometer, the concentration is P of 1 equals to 2 milligram per liter, find P of x for x greater than 0.
Okay, I think I can do this. So we can start by writing dp by dx is equals to x by p plus p by x, where p is equals to vx. dp by dx is equals to v plus x dv by dx. After simplifying, we can write it as v plus x dv by dx is equals to 1 by v plus v. After separating both the variables, we can write it as v dv is equals to x by dx by x. After integration, 1 by 2 v square is equals to log x plus c. We will resubstitute v is equals to p by x.
Yes.
After resubstituting, and since we have to find the value, since we have given the value p at 1 is equals to 2, substituting this in the above equation, we get c is equals to 4. Therefore, p of x is equals to x root 2 log x plus 4.
Very good. We did it. Congratulations, Vasu. Now you know what homogeneous differential equations are used for.
Head
Cut.